Okay. Up to now, all what we studied will not be included for the final exam. For the final exam, will be included from chapter 5 to chapter 10. Okay, these chapters are short chapters actually. I have planned to finish 2 chapters today because the chapters are really short, and there are really a few rules in each chapter. Okay, in each chapter we have only a few rules. These all chapters are about approximation, approximate solution for a nonlinear equation, for interpolation, for integration, for derivative, for those types of functions and data. The first chapter in approximation, which is chapter 5 in our material, is about only an introduction for numerical methods. Okay, here we just talk about some types of errors and finding the most suitable approximate value for some values. Okay, here we use numerical method for those equations or integrals that you couldn't find evaluate we couldn't evaluate it analytically. For example, here integration of x squared dx, let's say from 1 to 2, it's easy and you could evaluate it. Okay, we have rules for finding this integration, which equals to x cubed over 3 from 1 to 2. Okay, which equals to 2 cubed over 3 plus 1 cubed over 3. This is easy. Okay, what if we have integration of, let's say, sine x squared dx from 1, let's say, to 2? How about this one? In finding integration of trigonometric functions, we must have derivative of its angle. Here, derivative of the angle is 2x, that you cannot construct it. Okay, we have no derivative of the angle in the outside of the function. So this is difficult, or it's impossible to find this integration analytically. For finding this, we need to use a numerical method. Okay, so numerical method is used for those equations that cannot be evaluated analytically. Here we have some introductions that you can read by yourselves, and also here, if you have given a table, for example, here we have velocity for different times. We have this table is the velocity at different times. At 0 time is 0. I mean, velocity is 0 at 0 time. Is velocity at secant 1 is 0.5. At secant 2 is 1. At secant 3 is 1.5. How about the velocity at, let's say, it's asking for 2.7. What's the velocity at 2.7? Here, we have no time 2.7 in the table. How about velocity at 3? Velocity at 3 is 1.5. At 3 is 1.5. And at 2 is 1. At time to be 1, its velocity is 0.5. How about velocity if time to be 2.7? Here we cannot find it. Okay, in this case, we need to use a numerical method for finding it. Here we study interpolations for finding or for evaluating these type of points. These are nothing. Actually, you just need to read those, which I left above. Now we have types of errors. In this chapter, we just talk about types of errors. First, we have truncation error. Truncation error is used for, let's say, infinite series. To evaluate an infinite series, we cannot find the sum of infinite values. We cannot get infinite values. What we do, we ignore some terms, okay? Or we just take a few begin terms and then ignore the rest. We say that value which we get is an approximate value. For example, in finding 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus go up to infinity. To evaluate this, what you do? Maybe take these 4 first terms. We find this and we say the result is the sum of these approximately. We say the result is approximately the sum of these few terms that we took, which are at the beginning of the series. Here, in neglecting these terms, this process is called truncation, okay? The error that we have here is called truncation error. Truncation error. We now have another type of error, which is rounded error, round off error. For example, here 7.456. If you want to round it for 1 decimal point, means we leave 1 decimal point and ignore others or delete others. In this process, what we do here, it's asking for finding the rounded error for 7.456. Okay, what we do? We need to first write down 7 points. This is the first decimal point, so you must have only 1 decimal point. We look at the next decimal point. What's the next decimal point? It's 5. If it's 5 or more, we add 1 for this 4, so it becomes 5. Okay, so this the 7.456 approximately is 7.5. Okay, this is approximate value. What's the error here? The error could be obtained by subtracting the approximate value from the exact value, okay, or the original value. How about if you have 3.10235? What if we want to round it to 3 decimal points? How to round it to 3 decimals? Look, we write down 3 points. We write down the first 2 decimal points, 1 and 0. The third one, we look at its next decimal point, or we look at the 4th decimal point. What's it? It's 3. It's less than 5. We don't add 1 for the third one. We write down the same as the next decimal point is less than 5. We say it is 2. So it's approximately that value. This is rounding of error, okay? Or this is approximate a rounded value for that given value, okay? To find the error, we say error is the exact value minus approximated value, okay? It's exact value minus approximated value. In the case here, if this 3 to be, let's say, 6, what we do in that case? We add 1 for the third one, okay? It becomes 3.103. In that case, we add 1 for the third decimal point, as it's asking for rounding it for 3 decimal points. Generally, here we have absolute error. We say absolute error is always less than or equal to a half times 10 to the power minus k, where k is the number of decimal points that you round to. Okay? Now, what here we apply this one. We say if we have, let's say, 3.2682. If we round it for, let's say, 2 decimals. If we round it to 2 decimals, what we do, we need to find it is rounded value, which is approximately equal to 3.2. Look, this is the second decimal point. We look at the next one. It's 8. It's greater than 5. So we say it's 7. 6 becomes 7 as the next decimal point is greater than 5. We say here the error is the exact value minus approximate value. It is exact value minus approximate value. This error is always less than or equal to a half times 10 to the power. Here, this k is the number of decimals that you rounded to. It is 2 decimals, so it's 10 to the power minus 2. The error must be less than or equal to a half times 10 to the power minus 2. So the maximum absolute error is a half times 10 to the power minus the number of decimals that you rounded to. We say number of rounded to 3 decimals points is its absolute error is a half times 10 to the power minus 3. So it is a half times 10 to 1 over 1,000. 10 to the power negative 3 is a half times 1 over 10 to the power 3. 10 to the power 3 is 1,000. We get this one. So the error must be less than or equal to this value. If you round a number to 3 decimal points. The errors that humans faced are mathematical equations or models, errors from mathematical equations or models, also computing tools or machines, and error in the original data. There may be error in the original data. To find the error, we say, as I said before, it's always equals to original value minus approximated value, or exact value minus approximated value, true value minus approximate value. This could be original or exact. Okay. We say error is true value minus approximated value, and it's denoted by epsilon. This is epsilon. Is equal to alpha, which is the true value or exact value or the original value, minus the approximated value. This is how to find the error. Okay? And absolute error is the absolute value of that amount. We just take absolute value for both sides. We say error is exact value minus approximated value. And absolute error is the absolute value of the exact value minus approximated value. And you have another type of error, which is relative error. Here, the above ones, these are This is round of error. This is actually a round of numbers, not error. Here it's not an error. Error is exact. It's always exact value minus approximate value. Okay, this is a rule for finding approximate value for a given value, and also this one, truncation error. In the truncation one, this is a type of approximating value for an exact value. But we have these two or three, let's say. We have error, which is true value minus approximate value. Absolute error is the absolute value of true value minus approximate value. And we also have relative error. Relative error is true value minus approximate value dividing by true value in an absolute value. That's all in an absolute value. Alpha represents the true value. Alpha prime or alpha dash is the approximate value. So the relative error is exact value or true value minus approximate value divided by true value. Here, in this example, it says compute the absolute error and relative error for this one. If this is the true value and this is the approximate value, both are given. Both true value and approximate value are given. It says find both absolute error and relative error. So absolute error here, I am writing down above here. Absolute error. Absolute error is the absolute value. Oh, yeah, absolute error is absolute value of true value minus approximate value. Okay? Which equals to, what's the true value is this one. And this is the approximate value. If we subtract true value from approximate value, what we get? We get 0.00159 Okay, its absolute value is itself. It is 0.00592653898. This is absolute error. This is absolute error. To find relative error, what we do? We say epsilon REL. We always write down denoted by this. Absolute sub real, REL, relative. This equals to true value minus approximate value all dividing by true value. True value minus approximate value is 0.000159265358898.
Can we also change one that can say 1 minus approximate value?
One minus, no, it's not true. Look, let's take an example. Let's see if we have 1 minus 2 dividing by 1. Okay, 1 minus 2 dividing by 1. It equals to what? Negative half, which is half. Is it? How about if you have 5 minus 2 divided by 5? It's 305. Are these equal? No. So you cannot change it. Okay? If the true value changes, it will be changed. Okay? as it's not multiplication. If it's multiplication, yeah, you could. If we have alpha times alpha prime over alpha. In this case, if it's multiplication, these two cancel each other. So you just get the approximate value. So now we say true value minus approximate value is 0.00159265358898. Dividing by true value, which is 3.1415926535898. Just divide it, you get those. Okay? So the result is called the relative error, which you should divide these two. This is the relative error. This is how to evaluate relative error and truncation error for a given value, for both, if you have given both true and approximate values. Here we have some examples. It says find the error value and relative error if the exact value is n and approximate value is little n. This value is the exact value, capital N is the exact value, and little n is approximate value. Here, it's actually absolute error. It's absolute error. It's missed there. Here, for absolute error is exact value minus approximate value and absolute value. And relative error is exact value minus approximate value dividing by exact value, which is 0.0057. Look, in both absolute error and relative error, in both, we have difference between them after 2 decimal points, means from the third decimal point, we have difference between these two. Okay, we have difference between these two types of error from the third decimal points. Look at this one. Here we have another example. It says n is the exact value and little n is the approximate value. We say the absolute error is 4 and relative error is 0 point followed by 5 zeros and then 4. There is a big difference between these two. Okay, there's a big difference between these two. So in general, we cannot say which of these is better. Okay, in some examples, absolute error is better, and in some relative error is better. It's a good method for finding the error. Okay. Look at this one. N to be this value, and little n, which is the approximate value, to be this. Here we find these both. As you see, this is smaller than this. Which one is better? Absolute error is better. Okay, in this case. But in the above one, look, as much as the error is smaller, means that's better. Okay, this one is better. So relative error here is better. Relative error decides if our approximation is a good approximation or not. If it's close to zero, means it is a good approximation. Look at the above one. in the above example, the relative error is 0 point followed by 5 zeros then 4. Okay? This is a good approximation actually, as the relative error is too small. It's so small, okay? But here, the relative error is 0.25. It's not small. It's not a small value. Okay? For error, 0.25 is a really big value. It's too big. So this approximation which is used for this one is not a good approximation. But the above one is a good approximation. Okay? Relative error decides if the approximation is a good approximation or not. Okay? If it's close to 0, means it's a good approximation. But if we have, let's say, if you have non-zero values in the first few decimals, means it is not a good approximation. But if the first non-zero value is after second, third, fourth, those decimals, means it's a good approximation. If the relative error to be, let's say, 0.1 to this is not a good approximation, as the first decimal point is non-zero value. And this one 0.00, or let's say 5. This one is a good approximation, as the third decimal point is a non-zero value. Okay? Yeah, this is the absolute relative error. The maximum absolute relative error is a half times 1/10 to the power n. This is the maximum relative error. So if the relative error is less than that value, means it is a good approximation. If the relative error, if absolute value of the relative error is less than 1/2 times 1/100, and 1/10 to the power n, n is the number of decimals that you rounded to. Okay? If the absolute value of relative error is less than or equal to a half times 1/10 to the power n, where n to be the number of decimals that we rounded the number to, means it is a good approximation. If it's not, means it's not a good approximation. For example, here it says given a number rounded to 2 decimal points, rounded to 2 decimal points. So the maximum relative error is the maximum here. The maximum relative error is a half times 10 to the power -2, or a half times 1/10 to the power 2, which is 0. It is a half times 1/10 to the power 2, which is a half times 1/100, 1/200, which is 0.005. Okay. Decimals, it's given actually, should be given. Okay. Sometimes it's not given that rounded to that number of decimals. Sometimes the exact value is given, and also the approximate value is given. Here, if you have 3.15817, if it's given that, what's the absolute error for 3.15? let's say 16. To how many decimal points is this rounded to? It's 2. It's rounded to two decimal points. So you should know it's rounded to 2 decimal points. Okay, sometimes it's given like that. From the given information, be sure that you know it is rounded to which number of decimal points. Here, if you have N1, N2, capital N1, capital N2 to be two exact values, and little n1 and little n2 to be their approximate values. Epsilon 1, either at the first number is capital N1 minus little n1. Epsilon 2 is this one. And epsilon 3, which equals to, it is epsilon 1 minus plus epsilon 2. If we find the sum of these two, if epsilon 3 to be n1 plus n2 minus little n1 plus little n2. Okay, here means epsilon 3 is e1 plus e2, as we already found these two. Okay, that's it. A3 is n1 minus n3 minus n3, which is n1 plus n2 minus little n1 plus little n2. So the absolute error for 3, for the absolute 3 error is less than or equal to epsilon 1 in an absolute value plus epsilon 2 in an absolute value. That's all. Even for the difference, if A3 to be equal to n1 minus n1 minus, it equals to epsilon 1 minus, okay, this epsilon minus epsilon 2. Here we have an example. We actually have here we have this example. In this example, it says find the most accurate value for the following operation. Here we have this operation. It is the sum and subtract these values. Okay, it says where each number has been rounded to their decimal points. That means this is rounded to 2 decimal points. This one rounded to 3 decimal points. This value is rounded to 2 decimal points, and this one is rounded to 4 decimal points. To solve these type of questions, we must first find the exact value. The exact value is the sum and subtract these values. Okay, we say it is 3.69 plus 5.432 minus 2.37 minus 3.5214. This equals to 3.2306. Here it's calculated. Okay, this is the exact value. In the first step, we just find the exact value, which is this. This is the first step. Here in these type of questions, we just have 3 steps actually. Okay, this is the first step. In the second step, we need to find the modulus error for each of them. The modulus error for this one is 1 over 2 times 1 over 10 to the power n. N is the number of decimals. Okay, find it, which is 0.005. Okay, and for this one, for the second one, the second is Yeah, just this squared becomes power 3 and becomes power 3. It's for the second. For the third is 2, as we have 2 decimal points for the third one. And for the fourth one is to the power. Okay, that's it. It's how to find the modulus error we studied before in the previous slides. And now we need to find the modulus error. The modulus error is the sum of all errors. We find the error, the maximum error for each of them. Okay, and we find the sum of them. Here we have to find the sum of them, not this one plus that one minus that minus. We don't do that. Okay, we need to find the sum of them. Okay, this is the modulus error. After finding the modulus error, what we do? We add this modulus error to the exact value and subtract this modulus error to the exact value. It's their step. Okay, in the first step we find the exact values. In the second step we find the modulus error, which is the sum of all maximum errors. And then in the third step we just add and subtract this error, this modulus error. We add and subtract it for the exact value. Okay, and then we decide. Here it's the decision. We need to compare the errors. I'm sorry, the values that we got here after adding and subtracting the modulus error to the exact value. We get these two values, this one and this one. Now we compare these two both to the exact value. We compare these two both to the exact value. Now we need to count the number of similar decimals in total in both. Here it's 3.24115 and 3.2306. How many modulus errors do we have in similar? How many similar how many similar decimal points do we have? One. We just have, this is the first decimal point and the first decimal point are similar, but the second decimal point here is 4 and here is 3. It's comparing this to the exact value. Now we compare this again to the exact value. Here we also have one similar decimal point. We just compare the decimals from the beginning. Okay, we don't count all these similars. For example, if here we have 0 and here we have 0, it's not means they are similar. We need to just compare the beginning decimals, this one and this. Okay, we compare these to the exact value. In total, we have one decimal point. Okay, we have one similar decimal point. We compare these two to the exact one. In total, we have one similar decimal point. That means we need to round either this or this or this to what? We need to round it to one decimal point, or generally you could use the exact one. Okay, always use this one. After comparing these, we have one similar decimal point. Okay, means we need to round this to one decimal point. We need to round this to one decimal point. If we round it to this decimal point, to one decimal point, we look at the next decimal point. If it's less than 5, we just delete the rest of decimal points. We leave the first decimal point. But if this one, if the next decimal point is greater than or equal to 5, we need to add 1 for the first decimal point and then delete the rest of decimal points. But here it's 3. 3 is less than 5, so we just need to delete these decimal points. We delete these, and what we get we get 3 points. So the approximation of this exact value to 1 decimal point is this one. This is the best approximate value for this value, for this exact value. So the best approximate value is 3.2. That's it. Here we have just 3 steps. In the first step, we find the exact value. Then error means modulus error. And then add and subtract the modulus error to the exact value. In the first step, it's first step, second step. In third step, we just add and subtract modulus error to the exact value. Here, modulus error, exact value, plus minus modulus error. And then we decide what's the best approximation for the exact value. By comparing here we get 2 values. We compare these with the exact value. In total, we count the number of similar decimal points. So if the similar decimal points in total is 1, we round the exact value to 1 decimal point. If we have 2 similar decimal points, we round the exact value to 2 decimal points, and the rounded value is the best approximation. Here we have another example. I think we have this example here. It says it's the same, it's the same similar question actually to the one which we solved now. Here it says find the most accurate value for the following operation. This is our operations. Then, where each number has been rounded to their decimal points. We just follow those 3 steps that we followed in the previous example. First, we find the exact value, which is 1.172 minus 0.95 plus 6.3434 minus 1.383. And the result is this one. Here, this value is rounded to 3 decimal points. This one is rounded to 2 decimal points. This one is rounded to 4 decimal points. And this is rounded to 3 decimal points. Here we find the error for each. And if the sum of errors for the first one, here, that's it. For the second, for the third, we have 4 numbers. So we need to find the error for the maximum error for each. And then we always find the sum of errors. Okay, we don't care about these operations if they are plus or minus. We always find the sum of errors for the modulus error. For finding the modulus error, we need to find the sum of all maximum errors. So it is 0.00605. Now we need to add this one for the exact and exact minus that value. Okay, we add and subtract that value to the exact value. Okay, we add and subtract the modulus error to the exact value. Here, this is the exact value plus the modulus error. This take the exact value minus the modulus error. We get these 2 values, this and that. This the third step. Now we decide what's the best approximation for that exact value. What we do, we compare this to the exact value. How many similar decimal points do we have? Here it's 1 and then 8. Here we have 1 and 8, and others are different. So here we have 2 similar decimal points. How to so how many similar decimal points do you have here? Only 1. You only have one similar decimal point. The next decimal point is 8 and here is 7. So it's different. We have one. How many in total do we have? So we have only one. We have only one similar decimal point between this and both of the others, between the exact value and the values that you go from adding and subtracting the modulo 0 to the exact value. We have only one similar decimal point. Now, we need to round this to one decimal point. Here, this is the first decimal point. We need to round it to that one. We look at the next value. The next value is 8. What we do, we add 1 for the first one and we delete all what we have in the right hand side of the first decimal point. Here we add 1 for this one and then we delete these. As this one is 8, that's why we add 1. If it's less than 5, we don't add. If it's 5 or greater, you have to add 1 for the specified, for the required decimal point. Here we need to round it to one decimal point, so that's it. Okay, so it's approximately 5.2. Okay, and we delete the rest of decimals. Now this 5.2 is the best approximation. The best approximate value is 5.2. This is how we do this. In these type of questions, we just follow those 3 steps. So it's the end of this chapter. We now have chapter 6. In this chapter, we just talk about solving nonlinear equations numerical. In this chapter, we study 3 methods. We study 3 methods, which are bisection method, secant method, and Newton method. We study these 3 methods for solving a nonlinear equation. Here, if we have, let's say, it's written here, I think. That's it. That's all what we talk about here. Solution for nonlinear equation, then intermediate value theorem, IVT, which you all have studied in high schools. Then we have these 3 methods for solving nonlinear equation, which are bisection method, secant method, and Newton-Raphson method. Look at this equation. This equation is a linear equation. We could solve it, and we could get an exact value here. The solution here will equal to 0, and then x is 2. We get that x is 2. So this is the exact solution. If the equation has an exact solution, so we don't need to use numerical methods for solving it, for finding the numerical solution. We also here, we could factorize it, make it into 2 brackets, then find values of z. Okay, these equations have exact solutions. What if we have to the power 4, to the power 3, and these we cannot make it into brackets. Even here we have methods for solving these. We have Cardano's and Ferrari methods, which are 2 complicated methods for solving polynomials of degree 3 and 4. These also could have exact solutions. But how about this one? If we have f of x to be 3x squared sine x minus 2x. How about this one? Can we solve it? No, we cannot. We cannot find exact solution for this equation. What we do? We need to use numerical methods. For these type of equations, we have 3 methods to solve. We actually have 6 to 8 methods for solving these type of equations, but you just study 3 of them. Here, in this course, we just study 3 of them, which are bisection method, secant method, and Newton-Raphson method. We have these three methods for solving this type of equation. And here, these three methods are divided into two types. Bisection method, we have both are iterative. Actually, both are iterative methods. All are iterative methods. But the first one is interval iterative method. For bisection, we work on the interval. We work on an interval for finding the solution. But in both secant and Newton, we work on only one point. It's point iteration method. These two are point iteration methods. But bisection method is interval iteration methods. Now, for intermediate value theorem, we say intermediate value theorem is used for checking an interval to have solution of an equation in it or not. Here, let f of x to be, let's say 3x squared minus 8 sine x. If you have this equation, and if you have given this interval 0 to 2, to check if you have a solution for this equation in this interval or not, we use intermediate value theorem. We use intermediate value theorem to check if we have any solution of this equation in that interval or not. How? What we do? We first replace 0 here in the equation. Okay? We evaluate the equation at both endpoints, at 0 and 2. If we get two values with different signs, if the results have different sign, means we have a solution for that equation in the given interval. If both have the same sign, if both are negative or both are positive, means we have no solution for the equation in that interval. This is intermediate value theorem, actually. It's just to remind you, and I'm sure that you all have studied. Look, if we have, let's say it's f of a. This is the curve of f of a. This is a and this is b. So it is f of x. Yeah, it's f of b. This is f of a and this is f of b. Let's say this is f of x. This is the graph of f of x. How to check if we have a root for f of x in the interval ab or not? We evaluate a in the function, and then we evaluate b in the function. We evaluate both in the function. If they have different sign, if one of them is positive and the other one is negative, means we have a root for this equation in the interval AB. Based on the graph, if we use the graph, as you see, here, this is f of a. F of a is positive. And this is f of b. F of b is negative. Means f of a and f of b have different sign. So we have a root for the equation f of x in the interval a. Okay? Even if you have here, this is f of b, it's negative. F of a is positive. Means f of x has a root in the interval ab. We have examples here. Let me check if it's the same equation or not. 0, 1, x squared 2x minus 1. Yep. The equation here is x squared plus 2x minus 1. It says use intermediate value theorem. Check whether contains a real root in the interval or not for this equation. This is the equation. The equation is given in the solutions. Okay. It says use intermediate value theorem to check if this function has a root in each of these intervals or not. For the first one, for part I, we need to find f of -1 and f of 0. Okay, we check this one if we have a root of that equation in it or not. We say f of -1 is equal to, we replace each x by -1 in the given function. We check the function to have a root in the interval or not. So we evaluate both endpoints of the interval into the function. F of -1 is -1 squared plus 2 times -1 minus 1. It is -1 squared is 1 plus 2 times -1 is -2. Then minus, which is -2. This is f of -1. How about f of 0? If you replace x by 0, you get 0 plus 0 minus 1, which is -1. Both have the same sign. Both are negative. Means this equation has no root in this interval. The equation has no root in the interval. Check the second one. For this interval, we need to find f of 0, which is -1. We already found it. And f of 1. F of 1 is 1 squared plus 2 times 1 minus 1, which is 2. Look, one of them is negative. This is negative, and this is positive. We say f of 0 times f of 1 is -2, which is less than 0. If the multiplication of their evaluations in the function is less than 0, means one of them is negative and the other one is positive, or both have different sign, means we have a root for the equation in this interval. For that interval, we have a root of the equation in it. For this one, we do the same. Okay, we just check both boundaries. If they have different sign, I mean, we evaluate both boundaries into the function, into the given function. If the results are have different sign, means the equation has a root in that interval. Okay, if they have the same sign like the first case, means they have no root, the function has no root in the given interval. That's all what you have done here. Yep. If t equals to 0, so means that value is the solution. Means the value is the solution. Look, just a moment. Let me check. If we have f of x to be x squared minus, let's see 1. To check if this equation has a root in 0 1 or not. Okay, we replace 0, we get -1. F of 0 is -1. How about f of 1 is 0? 1 is actually a root of the equation. 1 is the root for the equation. We say the solution or the root for the equation is, the solution for the equation is 1. Okay? In this case, to check this interval, take a value less than 1. Let's say 0.9. Check it again. Okay? Check it again. you'll see if there is a solution. Okay. We now have bisection methods. Bisection method is a numerical method which is used for solving a nonlinear equation. We must first check the intermediate value theorem. We must check if the interval has a root in or not. Okay? We cannot use an interval in which there is no root for the equation in it. In that case, it's diverge. We never get the solution in that interval. For example, if we have f of x to be any function and the interval AB, if f of A and f of B are the same, I mean have the same sign, means there is no root for f in that interval. So if we look for the solution in that interval, we never get the solution. We never get a solution, as there is no solution in it. Bisection method is an interval iterative method. It's an interval iterative method. We always work on in an interval. If we take this interval as the initial one, if this is our initial interval, if in that interval we have no solution, so we never get the solution in that interval. Okay? So we have to first check the intermediate value theorem first. We must have solution for the equation in the given interval. And then the root can be obtained through midpoint of AB. I'm going to tell you what's the procedure. Here, we need to find a new interval. If our initial interval to be AB. This is given in the examples. Okay? The interval is always given in examples. Then, to find a new interval, we are going to reduce this interval till we get a really, really small interval. Okay? Here, we need to find a new interval. First, we have to find C, which is the midpoint of A. Which is the midpoint of AB. We say C is A plus B dividing by 2. But here we already checked this. Let's say f of A to be less than 0. We checked this. As we said in the first step, we need to use an intermediate value theorem to check if we have solution in it or not. We already know what's f of B and what's f of A. We know their sign. Let f of A to be less than 0 and f of B to be greater than 0. Then, to find the new interval, look, we said we have A, B. We find C here. We must reduce the interval to a half of it. The new interval is either this interval, I mean CB, or AC. It's either these two intervals, the new interval. Which of these should we choose? We must first find sine of C. We must first find sine of C. If f of C is less than 0, we take C with the one with the end point of the previous interval, which has positive sign. Which of these has positive sign? B means our new interval is C and B. What if C is greater than 0? What if C is greater than 0? If C to be greater than 0, then we return to the previous interval, the sign of its endpoints. in the function. The sign of A is negative. The sign of B is positive. We must always have an interval in which the sign of both endpoints are different. Here, f of c is greater than 0. We cannot take B as both have the same sign. Both are greater. What we do? We take A. So our new interval is A and C. And C is between them. So if we pick A, it's A and C. If we pick B, it's C and B. Okay? Then again, in the next step, we work on this example, on this interval. We find its midpoint. We say, let's say D is A plus C over 2. Now we find sine D. We find sine D. If f of D is less than 0, we took this is D is between them. We took this with one of these two to be the new interval. Which one? The one which has a positive sign in the function. Okay? That's it. We'll repeat it. Okay? Sorry? Or which root to be 0?
When we find the equation, interval of the equation, and our answer gives us 0. In that case, we use the bisection method.
No. Bisection method is used for solving any nonlinear equation. Okay? It's just the one you mean I have written down here for f of x to be x squared minus 1. You mean that? It's just explanation for the student. I give it to you. Yes. We must first use IVT. Okay? In each iteration, we use IVT. Okay? In each step, in each iteration, the interval must satisfy IVT, intermediate value theorem. That's it. This is just now. When we stop here, we stop if the difference of these two, the difference of both endpoints of our last interval is less than epsilon. Epsilon is given in the examples. Epsilon is given in examples. It's always given in examples. It says, it may say to 3 decimal points, to 4 decimal points, to 2 decimal points. Okay? So that's it. This is a case. And also, you could use f of last value that you find was the midpoint of both endpoints if it's less than epsilon. Either this or this one could be used for stopping the iterations. If it satisfies this or that one, we stop the iterations. To find the number of iterations, we could use this formula. To find the number of iterations, we could use this formula. Here, we need to find n. In this formula, we should find n. We first simplify this. We multiply both sides by 2 to the power n. We get b minus a less than or equal to epsilon 2 to the power n. And dividing both sides by epsilon, we get b minus a dividing by epsilon less than or equal to 2. To get n, take length for both sides. Take length for both sides, length of b minus a of epsilon less than or equal to n. So n, which is the number of iterations, is greater than or equal to this value. Okay? This is how to find the number of iterations. Now we have an example. In this example, it says, suppose we have this equation. The root is obtained through bisection method that lies in this interval. This is our interval. And approximates to 2 decimal places. 2 decimal places of accuracy. Check whether f satisfy intermediate value theorem or not in this interval. How to check? Here we check the intermediate value. We need to check if at these 2 endpoints, we need to check the function at both endpoints of the interval. We have to find f of 0, which is -5. And f of 1 is which one? Okay. Look, f of 0 is negative. F of 1 is positive. So it satisfies intermediate value theorem. It satisfies intermediate. It's just asking for checking whether it satisfies intermediate value theorem or not. So look, it's done by bisection. Okay. Now we solve it by bisection. Okay, it's done by bisection. So you must first check the intermediate value theorem. F of a times f of b, which is 0 and 1, is -5, which is less than 0. Or you could say one of them is positive and the other one is negative. So we say it satisfies the intermediate value theorem. It satisfies the intermediate value theorem. Then, for solving it by using bisection, what we do? We just work on the function and the interval. We just work on the function and the interval. In the first iteration, let's write down iteration 1. We may have 10 iterations, 20 iterations. We may have 3 iterations. We may have 5 iterations. Okay, it depends. It depends on the question. For the first iteration, what we do? First, before we starting the iterations, we must check the intermediate value theorem. We checked it and satisfies the intermediate value theorem. Means we have a root for the function in the interval 0 and 1. If it does not satisfy the intermediate value theorem, we cannot use bisection for solving it. We cannot use bisection for solving it. Now, we need to find the midpoint. What's the midpoint here? C is 0 plus 1 dividing by 2, which is 0.5. Okay? Now, we evaluate C in the function. We evaluate C in the function. F of C is 0.5 to the power 3 minus 3 times 0.5 squared plus 8 times 0.5 minus 5. The result is negative. Yeah, the result is negative. It's less than 0. We just need sign. We don't need its exact value. Okay? It's less than 0. As it's less than 0, with which of these two should we take? With 0 or 1? F of 0 is less than 0. F of 1 is greater than 0. As f of the midpoint is less than 0, we must take it with the positive. With 1. We take it with 1. Now, the new interval is 0.5 and 1. Now, in the next step, we do the same. Let's find C again. Here, iteration 2. This is the end of first iteration. Iteration 2. We need to find C again. C is 0.5 plus 1 divided by 2, which is 0.75. Is it? Now we find f of 0.75. F of 0.75. If this greater than 0, we take it, look, here, f of 0.5 is negative. F of 1 is positive. Is it? That's it. F of 1 is positive. F of 0.5 is negative. Just write down on it to don't return for evaluations always. Just from the interval, you could decide what's the new interval. F of 4.5. If it is less than 0, what's our new interval? With 1. It is 0.75 and 1. Again, we do it again and again and again. Until that f of last C, if f of C is less than 0.05 as 2 decimal points, yeah, or 5, or f of, sorry, no, or the interval, in the interval, the last interval, A minus B, in the last interval, is less than epsilon, which is 0.5. If one of these is satisfied, we could stop. And you could always use one of them in each step. Look, in the first step, f of C, it is, it's an amount, okay? You have to have calculators in exams, okay? You must have calculators in exams for the final exam, even for quizzes, okay? As you have many evaluations. So we need to find f of last C. F of C here, find it. Compared with the given error. Here, it says approximately to 2 decimal places. Okay? It may given as epsilon is 0.05. This may given. It's the same. The error, I mean, f of C must be less than this value, and then we stop. We are going to be continue until we get that f of C is less than this value, or the length of the interval is less than this value. We stop at that step. In the next steps also, it satisfies that condition. Look, that's it. This is what we do here. These are iterations. Iteration 0, 1, 2, 3, 4, 5. Iteration 0 is the one which is given. It's the interval which is given. You have that interval. In the second iteration, we go this interval, 0.5 and 1. In the third one, we go 0.75 and 1. And then we are going to be continue till we get that. The difference between these two, if we subtract these two in an absolute value, it must be less than the error, 0.05. Okay? It must be less than 0.05. Here, it's 3 decimal points taken actually. For the solution, in the solution, 3 decimal points taken. Here, it is round to 3 decimal points. But for the given example, you should stop here, as this is less than 0.05. Is it? we stop there.
What about the above? What about negative?
No, absolute value. We always take its absolute value. Yep. We said f of x, f of c in an absolute value must be less than absolute. Okay? So these two are extra steps actually. You don't need to do this. For this example, you should stop here in step 5. In iteration 5, it's enough. So in iteration 5, we get that 0.782 minus 0.813 is less than 0.05. It's less than this value. Or f of c at that point is this one, which is less than 0.5. You could use one of them. You could check one of them. Okay? And you should do this in all iterations. You may get the result in only one iteration. Okay? In the first iteration, check. In the second iteration, check it. Before you start the new iteration, you have to check this. If it satisfies the requirement or not. If it satisfies, you stop. If not, we start a new iteration. Then, in the new iteration, we do it again. If it satisfies the requirement, means if f of c is less than the given error, we stop. If not, we are going to be continuing. And always, if the error is not given, and if it says rounded to that number of decimal places, use 0.5. Okay, for 4 decimal places, it is 0.0005. Okay, for 2 decimal places is 0.05. For 3 decimal places, it's 0.05. That's it. Always do this. So this is bisection. It's all about bisection. It's really easy. It just takes time. Questions here in this chapter all takes time. It's all our iterations and many calculations. Okay? Try to solve examples by yourselves to do it faster in exams. As much as you solve questions by yourselves, you will solve the questions faster. Okay? Now, here, the last value which you get for C, the last value which we get for C is the approximate root for the equation. It's the approximate root for the equation. Here, this is C value. So this one is the root for the given equation. It says find the root of this equation in that interval. Find the approximate solution for that equation in that interval. You should provide the solution. You should provide the solution. How? It's the last value of C which you get. In that iteration which you stopped, take C value, which is the approximate solution for the given equation. Here, 0.79775 is the approximate solution for the given equation in the interval, in the given interval. But here, look, this one is taken actually. This is C value. Okay. Sorry, this is C value actually in the previous one. It's 0.798. So that is the approximate solution for the given equation. We finished now. Okay. It's enough for today. You know, we have this is week 9. We have 6 more weeks. We have 6 more weeks, and you only have 4.5 chapters. Yeah. We just have, this is half of chapter 6 and 7, 8, 9, 9 and 10. We have these 4 chapters left. So we will finish. Yep, sure. So that's enough for today.